We now take up the last major topic of this course. The subject is intractable problems. These problems are decidable, but colloquially they are said to be problems that take at least exponential time as a function of their input size. The reality is a bit different, but they are problems for which there is an overwhelming amount of empirical evidence that these problems take exponential time, although no solid proof of that belief. If a problem does take time that is exponential in its input size, then that means it can in practice only be solved for small instances. Suppose to be concrete that the time it takes to solve an instance of size n is 2 to the n. Then doubling the speed of machines makes essentially no difference in how large an instance you can solve. It adds 1 to the size n that you can solve in a fixed amount of time. Using 1,000 machines instead of 1 has the effect of adding 10 to the size n. And using 1,000,000 machines, each 1,000 times faster than today's machines, adds 30 to n. You never get to really big sizes of problem instances that you can solve. As a result, it is generally accepted that in order for a solution to a problem to be considered usable in practice, it has to run in less than exponential time, and in particular in polynomial time for some large polynomial. While an algorithm that runs in some large polynomial time, like n to the 1,000th power, is no more practical than one that runs in time 2 to the n, we find in practice that if a problem has a polynomial algorithm at all, then it has an algorithm that runs in some low-degree polynomial like n squared or n cubed at the most. In this lecture, we introduce several important preliminary concepts. We introduce the idea of a Turing machine that is time-bounded. It can only run for a time that is a known function of its input size before it has to stop and tell us whether it accepts or rejects. We introduce the class P of problems or languages, it's the same thing of course, that can be solved by a Turing machine that runs in polynomial time as a function of its input size. We also meet the class NP, which is problems that can be solved by a Turing machine that is non-deterministic, but has a polynomial time bound along each branch. Finally, we'll learn about polynomial time reductions, which are reductions where the transducer runs in time that is polynomial in its input size. These are used to show one problem intractable by reducing a known intractable problem to it. We say a Turing machine is T of n time-bounded, where T of n is some function of n, like n squared or 2 to the n. If given an input of length n, the machine always halts in at most T of n steps. We allow the Turing machine to have several tapes. In some circumstances, we allow the Turing machine to be non-deterministic, although in that case we will specify that it is a T of n time-bounded, non-deterministic Turing machine. Also in that case, we mean that any sequence of moves of the non-deterministic machine is no longer than T of n. In practice, a deterministic multi-tape Turing machine is close to the idea of an algorithm that runs in time proportional to T of n, or big O of T of n. That is, while some algorithms take longer on a Turing machine, even multi-tape, than on a real computer, these are rare. Moreover, when there is a difference, the difference tends to be small. A Turing machine M is said to be polynomial time-bounded if it is time-bounded by any polynomial. It could be linear, quadratic, cubic, or n to the 1,000th power, as long as it is some polynomial. The languages that are accepted by polynomial time-bounded Turing machines form the class P. Now, P is defined formally in terms of Turing machines, but it could just as well have been stated as polynomial time on a real computer. The reason, which we address on the next slide, is that if an algorithm runs in some polynomial time on a computer, then it will run in polynomial time on a multi-tape Turing machine, or even a one-tape Turing machine, although the degree of the polynomial may be higher in some cases. That is, we saw a way to simulate a name value store by a computer. That is the part of a real computer that takes the most time when simulated by a Turing machine. But if a computer runs for on the order of T of n steps, then it can't store or retrieve more than T of n items in its memory. A Turing machine can simulate one lookup or insert into a name value store in a number of steps that is proportional to the length of the tape that holds the store. But that length is proportional at most to the number of steps the computer has taken, which is T of n, and thus the Turing machine takes at most T squared of n of its own steps. If T of n is a polynomial, then so is T squared of n. The The exponent grows, of course. A cubic algorithm on a computer might take time proportional to n to the sixth on a Turing machine, but it's no worse than that. And since we're trying to divide the world of problems into those that have polynomial algorithms and those that don't, we can think Turing machine or computer, whichever is more convenient. As you might expect, when simulating a program, it's best to simulate a Turing machine. But when devising an algorithm, it's best to think about a computer program. Here are two examples of problems or languages, which is the same thing, in the class P. For each context-free grammar G, there is an algorithm, the CYK algorithm, that takes an input string W and tells whether W is in the language. The running time of this algorithm is O of n cubed. The second problem I want to talk about is finding a path in a graph. Here we're given a directed graph that is a list of its nodes and arcs. We are also given one node as the source node X and another as the sink node Y. The answer is yes if there is a path in the graph from the source to the sink. Graphs must be coded in a finite alphabet, which should not be hard to see. Represent the ith node by n followed by I in binary, and represent an arc by a pair of nodes, the tail and the head of the arc. Use two special symbols to indicate the source and sink nodes. Note that if there are m nodes, it takes order log m space to represent one node, so n, the input length, is actually somewhat greater than the number of nodes and arcs, but the difference is unimportant since we are only worrying about polynomial versus not polynomial. Depth first search answers this question in time that is linear in the number of nodes and arcs. On a Turing machine, you might need order n squared steps, and for one step of the depth first search, you have to locate on the input the arcs with a given node as the tail. That could require that you run all along the tape just to simulate one computer step, but n squared is still a polynomial, so as far as membership in P is concerned, n squared is just fine. And just to make sure, when we talk about polynomial time, we include every running time that is less than some polynomial. That is, the definition of P only requires that the language be accepted by some Turing machine whose running time is bounded above by some polynomial. For example, there are many algorithms that run in times like order n log n, but that's less than n squared, so the problems solved by algorithms like this are surely in P. Before proceeding, I want to examine in detail a problem that seems to be in P but really isn't, and I want you to understand why. This is really important in understanding what the class P really means. The problem called knapsack is this. We're given a list of n positive integers. The answer to this instance of knapsack is yes, if and only if we can partition the integers into two groups whose sums are equal. For example, if the integers are 1, 2, 3, and 4, then I can partition them into 1 and 4 in one group, and 2 and 3 in the other group, and the sums in each group will be equal. Incidentally, the problem is called knapsack because of the view that the integers are weights of items, and two hikers want to divide the items between their two knapsacks so each carries equal weight. At first glance, we can solve the knapsack problem by a polynomial time dynamic programming algorithm. That is, we maintain a table of all the differences in sums we can achieve by partitioning the first j-1 integers. When we incorporate the jth integer, we take each possible difference and both add and subtract the jth integer, thus getting two new possible differences. After looking at all integers, we see if 0 is a possible difference. To be more precise, for the basis we consider none of the integers. Then the table has true for 0 difference and false for all the other differences. For the induction, suppose we have a table for the first j-1 integers. We build a new table to reflect the partitions of the first j integers. Initially, each entry in the new table is false. But suppose the jth integer is I sub j. For each difference m that was true in the old table, set the entries for m plus I sub j and also m minus I sub j to be true in the new table. Let's compute the running time of this algorithm as a function of the sum of the integers. Let's say that sum is s. We need order s space to construct a table for one value of j, since the differences must be in the range minus s to plus s. And it only takes order s time to construct each table from the previous one using a real computer. Maybe it's order s squared on a Turing machine because we have to move the head a long distance to write each entry. But again, when designing algorithms and worrying only about whether something is polynomial time or not, a real computer is the right model to think about because the programming details are generally easier. Okay. Note that n is equal to or less than s since the integers are each positive. That is, the sum of the integers is at least equal to the number of integers on the list. Thus, we can build a table that corresponds to the set of all the integers in order s squared time, s for each of n different tables. We then look in this table and see if 0 is true. If so, the answer to the knapsack instance is yes, and otherwise it is no. However, that conclusion is actually deceptive. Although it is true that we just described an algorithm that runs in time no more than the square of the sum of the integers, and that algorithm really does solve the knapsack problem, it doesn't tell us that the knapsack problem is in P, and in fact it is almost surely not in P, as we shall see later. The reason this algorithm doesn't show knapsack to be in P is that membership in P requires that the algorithm runs in time polynomial in the input size. But we can't just define input size to be the sum of the integers in the input. The input size is always the number of cells it takes to write the input on a Turing machine tape. For the knapsack problem, this input length is not necessarily polynomial in the sum of the integers, as we shall see on the next slide. The longest input length occurs if we have n integers, each of whose values is about 2 to the n. If we write the integers in binary, the input to the Turing machine is order n squared in length. But a table then requires about n 2 to the n entries and at least that much space to write down. That is, the sum of all n integers can be around n times 2 to the n. We can't construct one table in time less than its length, so the total time of the algorithm is on the order of n squared times 2 to the n. But the input size is n squared, and n squared 2 to the n is not a polynomial function of the input length. By the way, we usually like to have n be the actual input size for the Turing machine. So if we substitute n for n squared, we can say the inputs of size n leads to an algorithm that takes time proportional to n times 2 to the square root of n. That is still not a polynomial. Thus, the dynamic programming algorithm we described, while it is really a good algorithm when the integers are of limited size, does not show the knapsack problem to be in the class P. There is another problem which we can call pseudo-knapsack. The question is the same, but the integers are represented in unary, not binary. That is, integer I is represented by I1s followed by some marker symbol to separate integers. This problem is in P, and the dynamic programming algorithm proves that. But it is not the classical knapsack problem where integers are represented in binary, the sort of rational way to represent large integers. The second important class of languages for our story is NP, the non-deterministic polynomial class. NP is defined in terms of non-deterministic Turing machines. The running time of a non-deterministic Turing machine is the maximum number of moves it takes along any branch. That is, by making any sequence of choices. If there is a polynomial bound on that time, then the non-deterministic machine is said to be polynomial time bounded. And the language or problem it accepts is said to be in the class NP. For example, the standard version of knapsack, where integers are represented in binary, is an NP. The non-deterministic polynomial time algorithm that solves this is fairly simple. First, it uses its non-determinism to guess a partition of the integers into two subsets. This can be done in time that is linear in the input length using 2 extra tapes for the 2 subsets. Then sum the subsets and compare. Say yes if this partition yields 2 equal sums, and this part can surely be done in time that is quadratic in the input size and can be done in linear time if you're clever and use a few extra tapes. Thus, standard knapsack is an NP. Note that this fact doesn't suggest a deterministic polynomial time algorithm, since it may take exponential time to simulate the non-determinism of the Turing machine. Are P and NP really the same class of languages? That is, can any problem that is solved by a non-deterministic Turing machine in polynomial time also be solved by some deterministic Turing machine in polynomial time, even if the degree of the polynomial was higher? This question was posed by Steve Cook in 1970. At first, it didn't seem all that hard or unlikely. After all, non-deterministic finite automata can be simulated by deterministic finite automata, even though the number of states might grow. And deterministic Turing machines can simulate non-deterministic ones. But the problem has proven to be very, very difficult, and mathematicians who once sneered at the question and assumed it was easy because computer scientists had thought it up, now recognize it as one of the most important mathematical questions, perhaps the most important unsolved question. However, there are thousands of problems that are in NP, but for which no algorithm in P has been found. And unfortunately, neither is there a proof that these problems are not in P. What we do have is a linkage of the large class of problems called NP-complete problems, which we discuss on the next slide. What we do know, then, is that either all these problems are in P or none of them are. So they mutually enforce the notion that none of them are, since many have been worked on for decades and no polynomial time algorithms for any of them have been found. So we're going to address the question of whether P equals NP by identifying complete problems for NP. Say a problem in NP is NP complete if the following is true about the problem. If the problem is in P, then P equals NP. That is, every problem in NP is also in P. It turns out that almost every problem that is known to be in NP but is not known to be in P is NP complete. There is only one well-known exception, graph isomorphism. Given two graphs, is there a one-to-one matching of nodes between the two graphs that makes the graphs identical? This problem is known to be in NP. Just guess the matching of the nodes in the two graphs and check that the right edges exist. But there is no polynomial time algorithm known, and neither is there a proof that graph isomorphism is NP complete. But graph isomorphism is an exception to what appears to be an almost general rule. If it is in NP and it isn't known to be in P, then it is NP complete. While the definition of NP completeness merely states that there has to be some way of proving P equals NP from the assumption that the problem is in P, there is a standard way of making such proofs, and it appears to be sufficient for all the NP complete problems that we know about. This method involves reductions of the type we talked about for Turing machines in general, but with the condition that the transducer run in polynomial time as a function of its input size. Intuitively, a complete problem for a class embodies, in some sense, every problem in the class. For example, post-correspondence problem embodies every Turing machine, even though it is hard to see PCP as involving computation. It seems to be about concatenating strings in constrained ways. So it might surprise you to know that each NP-complete problem, such as knapsack, embodies all non-deterministic polynomial time computation, even though the knapsack problem seems to be about anything but computation. So in order to show problem L to be NP-complete, we have to show that every problem in NP is somehow embedded in L. We need a transformation from every problem in NP to L, and this transformation has to be sufficiently fast that if we had a deterministic polynomial time algorithm for L, then we could use it to build a deterministic polynomial time algorithm for each problem in NP. We're going to define a polynomial time transducer. Notice that people frequently shorten polynomial time to polytime, and we'll start doing that too. So a polytime transducer is a deterministic Turing machine that takes an input of length n, runs for some polynomial number of steps p of n, and produces an output on an output tape. It is important to observe that although we do not restrict the output length, since the Turing machine only runs for p of n steps, it could not write more than p of n symbols. Thus, the length of the output of a polynomial time transducer is always polynomial in the length of its input. Here's a picture of a polytime transducer. It can have any fixed number of tapes. One is the input tape and one is the output tape. We argued on the last slide that the output length must be polynomial in the length of the input, but the real constraint on the polytime transducer is on how long it runs. It is not acceptable to have it run for time that is exponential in its input length, even if the output is short. Consider two languages or problems, say L and M. We say L is polytime reducible to M if there is a polytime transducer T that takes an input W that is an instance of L, produces an output X that is an instance of M, and the answer to L on W is the same as the answer to M on X. That is, W is in L if and only if X is in M. Here is a picture to help us remember what a polytime reduction does. On the left is the set of strings over the alphabet of L, divided into those that are in L and those that are not in L. On the right is the set of strings over the alphabet of M, also divided between M and its complement. In the middle is the polytime transducer T. Every string in L is transformed by T into a string that is in M. There can be strings in M that are not the target of any string in L. And every string not in L, but over the alphabet of L, is transformed by T into a string that is over the alphabet of M, but is not in M. Again, there can be strings in the complement of M that are not the target of any string in the complement of L. Formally, we say a problem or language M is NP complete if, first of all, it is an NP, and for every language L in NP, there is a polytime reduction from L to M. An important consequence of the fact that M is NP complete is that if M has a polytime algorithm, then so does every language L in NP. That is, the classes of languages P and NP are the same, or P equals NP. Notice that earlier we suggested that the definition of NP completeness was simply that the language had this property. Steve Cook's original definition of NP completeness was exactly that, and it is often referred to as Cook completeness. Cook concentrated on showing one particular problem, the question of whether an expression of propositional logic was satisfiable, that is, made true by some assignment of truth values to the propositional variables. But shortly after Cook wrote his original paper on NP completeness, Dick Karp wrote another paper that showed many of the classical problems that had been puzzling mathematicians, sometimes for centuries, were NP complete. Karp used only polytime reductions from the problem Cook had proved NP complete. Since then, it is generally accepted that the preferred definition of NP completeness is the one we gave here, the existence of polytime reductions. To make the distinction, this notion of NP completeness is often called Karp completeness. So here's the plan for proving certain problems to be NP complete. Here's all of NP. SAT, the satisfiability problem for propositional logic that we just discussed, is one problem in NP. Cook's theorem is that every problem in NP reduces in polytime to the SAT problem, so SAT is the first known NP complete problem. Cook also proved a restricted form of SAT called 3-SAT to be NP complete by reducing SAT to 3-SAT. We'll learn what the 3-SAT restriction is shortly, but in brief it is SAT restricted to expressions that are the AND of clauses with 3 literals per term. A literal is a variable or a negated variable, and a clause is the OR of literals. Then from 3-SAT we do polytime reductions to many other problems, either directly or indirectly. Each problem we can reach from SAT by a chain of polytime reductions is thus proved NP complete. But before we embark on this quest, let's make sure that polynomial time reductions work in the sense that they let us draw the desired conclusion about all of NP reducing to the target problem. So suppose M has a polytime algorithm, say running time Q of n for some polynomial Q. Let there be a polytime transducer T from some problem L to M. And let the time taken by T be P of n for some polynomial P. The output of T, given an input of length n, is at most of length P of n. So when we run the algorithm for M on this input of length P of n, the algorithm takes time Q of P of n. Note that a polynomial of a polynomial is a polynomial. The degrees of the polynomial are multiplied, but it's still a polynomial. We claim there's a polytime algorithm for L. Given an input W of length n for L, apply the transducer T to W. The result is an output X of length at most P of n, and more importantly, T takes time, only P of n, to produce this output. Apply to X the algorithm to tell whether it is an M. As we observed on the previous slide, this part takes time Q of P of n. Then return as the answer for W whatever the M algorithm says about X. The total time of this algorithm is P of n plus Q of P of n, which is polynomial if P and Q are. It is a correct algorithm because the fact that T is a polytime transducer from L to M says that the answers to input W and output X are the same.